never, ever, ever go back on a deal. Okay, so today let's talk about forces and measuring things with strain gauges and load cells. First thing I'm going to tell you, remember those little yellow P3500 boxes that they had to use in Mech Lab 1? I hate those things. I utterly hate those things. When you just hook up a bunch of wires and you press a button and a magic number pops out, you have no earthly idea what went into that number. Today, we're going to rectify that situation. We're going to go old school again, because that's what I do. And I'm going to show you where that number came from, and we're going to set up the circuitry that's actually in that box. Okay, let's start with the basics. Strain gauges. Okay, nothing more than a whole bunch of little lines, conductor lines. You stretch them, the lines get thin. Because there's less area to conduct the electricity through, the conductivity goes down and they become more resistant. Not by much, but just enough. Okay? And it's just the opposite if you compress them. So if I squish them in, I make the lines fatter, there's more area to conduct the electricity, they become more conductive. Just a little bit. When we go to set these things up, guys, we set them up in something called a Wheatstone bridge, which is that. So we have a resistor 1, a resistor 2, resistor 3, resistor 4, and we measure the voltage from the output of the bridge across the middle. Okay? This thing used to screw me all up when I was sitting in your chairs. I got so confused by this foolish thing. Until I realized a Wheatstone bridge is nothing more than 2 voltage dividers. That's all it is. Okay? And you know, that's the classic voltage divider 1 minus voltage divider 2, and you get the bottom derivation. That made things a lot simpler to think about. So if I put a variable resistor in there, let's say R2 is my variable resistor. Okay? So I can take and I can make the output value V1 by changing the variable resistance exactly equal to V2. And then I'm going to make R4 or R3 one of my strain gauges. So because I'm going to take V2 and I'm going to let it go up or down with a changing strain gauge, I'm going to get an AC signal out. Or at least something that can change polarity.
Hi students. In front of you is an example of a Wheatstone bridge. That is this protoboard right here. Okay, so we have a reference voltage being created on this side. That's going to remain constant. But we're going to use the multimeter to compare the output of this reference voltage to the output voltage of this potentiometer. So this pot can act as a voltage divider completely on its own. So let's watch what happens to the multimeter as it changes the value of the pot. Too much coffee. Okay, notice on the multimeter you're seeing a negative value. Okay. So that means that the voltage divider that I'm affecting right now is outputting less voltage than the reference with these fixed resistors. And I can also go the other way. So if I twist the pot in the opposite direction, I can get a positive voltage coming out of the Wheatstone bridge. This is very, very useful for when you're doing strain gauges. Now we can look at the sign of the output and know whether our output is tensile or compressive.
Okay, so that's cool. But digital electronics don't like AC. They don't like things that are flipping polarity. We got a way to fix that though. And the other thing I want you to know is that when we replace R4 with strain gauge 4, okay, we are not going to change that output voltage by much at all. I mean, really, really, really small changes in voltages. And that's where our op amp is going to come in. So we are going to use the INA 125P. And the thing that is cool about that is that the 125P is meant specifically to drive Wheatstone bridges and strain gauge bridges. You can wire it up so that if you have a perfectly balanced input, so let's say I've got 1 1/4 volts on the positive input, 1 1/4 volts on the negative input, it's going to output 2.5 volts, half of its supply voltage. And if I put in something that's more positive on the inputs, it'll go up from 2.5. And if I put in something more negative, it'll go down from 2.5. So all you got to know is where you're balanced about, and you can still get whether you're tensile or compressive.
Now let's continue our little experiment. I have the same Wheatstone bridge in front of you, right here, but we've added a couple things. We have cantilever beam set up right here with a strain gauge set up at the quarter bridge. The output of the Wheatstone bridge is going to this meter up here. And we've also added something new. We've added an INA 125P amplifier stage, which is right here. So let's put a 5-pound weight on the cantilever beam and see how much output we get from the Wheatstone bridge. Apply the weight. And I get 1.3 millivolts. Well, that's a problem. So an Arduino with a 10-bit analog to digital converter can read 5 millivolt increments. So this is not even one increment. And that is why we have this amplifier hooked up. The amplifier takes the small output from the bridge and enlarges it so that the digital systems can actually read it. The interesting thing about the INA 125P is that it puts 0 at 2.5 volts. So if you have no load, you get 2.5 volts out. As you start applying load, as we just did, let's see if I take the load away, it comes almost exactly back to 2.5 volts. This takes care of the polarity problem with interfacing with digital circuitry.
Okay, so pretty nifty. Problem comes, however, in balancing your bridge, folks. So we just saw that putting that 5-volt weight on there, that only made an output of 1.3 millivolts. If your initial balance is off by like 5 millivolts, you can completely saturate your amplifier. So the amps that I've been running in these demonstrations, they're taking that input signal of sub-millivolt, microvolts, And they're amping it up by a factor of 200, 600, 1,000, just to get a really good sensitive output signal. Okay, so balance is critical. And we can change the gain on the INA 125P. So I made this little circuit board right here. And normally you would solder in a gain resistor right there for R1. Well, I kept screwing up my boards and had to buy new boards. So finally what I did is I just ran these two terminals over to the gain resistor. And by having the gain resistor hanging out, okay, now I can change it and I can adjust more or less resistance to get more or less gain factor. So if you're going to be measuring forces as part of your experiment and you're saying, gee, you know, I've got too much signal, I've got too little signal, you can change that resistor right there to change your output. Okay, one of the other problems. So in MEE443 1, I'm pretty sure you guys did all quarter bridge stuff. Does any of that sound familiar? Shaking my head, yes? Okay, cool. Okay, but there's a problem with that. There's multiple problems with that. Okay, the first one is they're temperature sensitive. These strain gauges, all those little fine wires, if you warm those up, they become more resistive, just like a light bulb. If you cool them down, they get more conductive. And let's watch what happens.
Now I'd like to show you another problem with quarter bridge strain gauge setup. Watch the two gauges, and I'm going to put my hand on the strain gauge. I'm doing my best not to apply any force.
So just the heat of my hand is down for like over 100 millivolts after the amp.
Put my fingers on it. Take my fingers off it. So we've got a pretty good swing going on just from the warmth of my hand. And this can be eliminated by going to a half bridge setup.
Okay, so that little silly yellow box that they showed you in MEE443 1, that has no idea about temperature compensation. It can't. It doesn't know what's going on out at the sensor. Okay, the other problem with the silly yellow boxes is they don't know if they're looking at bending or tension when you're doing quarter bridge. And that's where today's little demonstration comes in. So I have the good old cantilever beam right here. And let's turn it on. Don't worry, I'm not going to make you do a stress calculation for the 47th time in your careers. So let me show you how sensitive this thing is. Balance. Oops, hand out of the way. So if I just tweak that potentiometer just a little bit, I am down at 50.9 millivolts. And if I tweak it just a hair, going up, going up, going up. Okay, that was actually what I wanted to show you. So I go from fully picked out to 48 millivolts, and I didn't move that potentiometer hardly at all. I might have moved it a 16th of a turn, maybe. So if you're trying to manually hand balance one of these Wheatstone bridges, do not drink a lot of coffee. All right, I'm going to try and bring it back to 2.5 volts. Almost. I went the wrong way, seriously. Okay. 2.3. I like 2.5. I don't know if I'm going to get there. Okay, I just bumped it. I didn't even try to turn it. .7. I'm going to call that good. So that's probably balanced within, a few microvolts. So if I grab this thing now, and I pull on it, come on. And I'm trying not to bend it at all. Or if I squeeze in, it is tension sensitive. Okay. I could have amped this up a little bit more probably. Because right now I've got a gain factor going of about 200. So let's see, we're at 2.64, I'll go in. Just going down. I pull it out, it should go up. Come on. Going up. So yeah, quarter bridge. You don't really know what you're measuring. So if you're worried about the difference between bending and tension, quarter bridge is not going to get you there. If you're in a situation where your sensor could warm up, you could be chasing drift all over the place, signal drift. But we can solve this by going to half bridge. So what I'm going to do to go to half bridge is I'm going to change S4, I'm going to have my strain gauge 4 and strain gauge 3 active. So now that change in resistance kind of negates each other. And the center voltage will stay the same. So it's going to look like this. You'll have S4 on the top and S3 on the bottom. A lot of what I'm telling you guys is coming out of this article from National Instruments. They did an excellent article on measuring with strain gauges. So I would encourage you to look at it. I also posted it in the class notes. Okay, so that's great. The other thing about half bridge, guys, is it doubles your output signal. So you get twice the sensitivity. And then you're probably thinking to yourself, okay, that's great. So if I make 2 of the resistances strain gauges, and it doubles my output, what if I just make them all strain gauges? Cool. Well, that's actually a thing. So then you get rid of the axial tension problem, not knowing whether you're in bending or tension. You get rid of the temperature sensitivity, and you get 4 times the output signal of a quarter bridge. And you know what? What's really cool about that? That is exactly what is in a commercial load cell. Okay. 4 strain gauges is exactly what's in a load cell. So what I'm going to do, let's change this out. So I've got the exact same board. This amplifier has the same chip in it. But this one I've got the gain turned up a little more. This load cell is a bending beam style or parallel beam style load cell. Let's turn it on. It's a 100 kilogram model, so I had to amp up the output just because I am not Superman and I can't bend aluminum that well. On screen. Okay, notice, no balancing, no balance resistors at all. I'm taking the output wires from the strain gauge, I'm going right into the amp. Now, normally, your load cells are pretty well balanced. I'm getting 2.4 volts out, so it's not perfectly balanced, but it's pretty darn good. So you have two options. There's external circuitry you could add to inject current and affect the balance, which, again, I posted those in the class folder. If you want to check that out, great. I mean, or you do what I do, and just cheat and say, I'm just going to do the subtraction in software. So if I grab my beam now and I try to bend it, should have eaten my Wheaties this morning. So if I try to bend it this way, and so I'm bulging the center out, it's going to go down. If I try going the opposite direction, come on, it goes up. But if I try to put it in compression, I'm surprised it moved that much. Okay, I think I was actually leaning on it. I think I'm just asymmetrically loading it. But it should be completely immune to compression. And with full bridge, you can do either bending or axial tension, depending on what you want to look at. And here's how you arrange the strain gauges. So for bending, you want to have all your strain gauges parallel to the beam. And for axial, you have to mix it. And here are your typical load cells. These are a bunch that I just happen to have in Crosby. So you've got what's called an S-beam up here. So you can grab those two eye bolts at the end and pull on it. This is a smaller parallel beam or bending beam load cell. This is the one I just showed you. And this is a compression style, a little squeezy disc type of load cell. They all work exactly the same way. And we could hook any one of those up to the INA 125 and it would work just fine. So really the only time that I would use strain gauges, folks, they're a pain in the butt to put on. They do work. But if I was going to do something like, say, verify an FEA analysis, and I wanted to look at a particular high-stress region, that might be a good time to use a strain gauge if you're trying to verify something else. Any other time, just go grab a commercial load cell and make your life easy. Because I assure you that soldering those little wires on, that is painful. Okay, and this is the one I just showed you. Again, when I was bending that 100 kilogram load cell, I had a gain of 1,000 going on. just to get a signal out of that. It's a big cell. I can actually amp this up enough. If I change the gain resistor and pretty much max out this op amp, okay, I can make this thing so that it can actually detect bending under its own weight, just hanging it like this. So you can get gains of 60,000, plus with an op amp. And this is all just the good old stuff from Mech Lab 1. So if you want to do quarter bridge measurements and actually get the stresses. For those of you that might need a strain gauge, I stock the MEE443s in Crosby. They have a gauge factor of 2.04, so you may need that number in the future. And this is just a good old example of how to do stress calculation from the quarter bridge strain gauge. The references. And last item, I guess we're going to be a short lecture today. So I was doing a comparison of quarter, half, and full bridge on this thing. I thought that'd be cool. But then I realized I was going to spend half the class time just sitting there changing wires, and nobody finds that interesting. But the takeaway message here, folks, I was using a gain of 189.76, and just take a look at the trends. So the bottom line is your quarter bridge. So as the load goes up on the cantilever beam, you're not getting a whole lot of output signal. When you go to half bridge, you get a whole lot more. And then the slope for the full bridge is actually 4 times what you were in quarter bridge. And that's really the only takeaway. And lastly, when I was doing the quarter bridge, my signal was only 0.2 of a millivolt. So it was a really, really small input signal. All right, that's the material for today, folks. Any questions? I started looking over some of your experiment submissions. In general, there'll have to be a little bit of negotiation on some of them. Some of you guys tried to do too much, some of you guys tried to do too little. I will do my best to get all of those back this week. And then we can get you guys off for testing and doing your thing. All right. If there's no questions, you're free to go.